So we're now in the second stage of problem solving. So here what we want to do is see how many ways such problems can be solved, and from there we narrow down to which one of those methods are likely to work, which one is easiest and most feasible. So as we get started, we can ask some very simple question. What type of a problem is it? It's of course a radiation problem. That's pretty obvious. It's talking about radiative exchange. So in radiation, we have done these three types of problem: emission and absorption at a surface, energy exchange by radiation only, and energy balance that includes radiative heat exchange. These are the three types of problems we have done. So let's see which one of this category this one falls under. So now in this step, we're trying to decide how many ways to solve this kind of radiation problem. So at this point, we do not know how we're going to solve this one, but we start from how many ways we can solve this type of radiative problem. So what would be handy is this map that we develop, that all radiative exchanges can be first grouped into two types for the purpose of this class: two surfaces and enclosures. Now this problem shows that it has this top surface, radiating surface, and it has the infant surface. So this is surface 1, let's say, and this is surface 2. So it certainly looks like it's a two surface problem. So it is unlikely it is an enclosure problem, because these sides are open. These sides are all open, so it's not an enclosure problem. So we now have narrowed down to it being a two surface problem. Also, only thing we have done for two surfaces is that the surfaces have to be black. This we have to make sure. Have we been given that? So let's look at the description of the problem. So this is a bit messy here, but you see in the description of problem, we see emissivity of both radiant heating surface and the baby surface is 1. So that is same as saying they are black. So now that we have these two choices, the next question we can ask, which one looks most feasible? Well, that's kind of obvious. There's only one choice for which there is a simplification, but it's really one choice. So most feasible, it's kind of irrelevant in this problem. Afterward, we can ask this question: based on the provided data, which one looks the easiest? So here we have to be careful. So this is one choice, and it shows that we can have a very gross simplification of this. So we have these two choices. Which one looks the easiest? Of course, this one looks the easiest. But here you need to be careful, because as it says, it's a gross simplification. This is only true when T1 is very close to T2. So how much error you make when T1 is different from T2 is of course depends on the problem, and as T1 gets farther from T2, the errors would be larger. So we cannot just use this gross simplification here if we are able to do the problem this other way. So let's see if we can do the problem this other way.